Okay, we're going to look at concavity and the second derivative test. So previous lesson, we had looked at the first derivative test and things like critical points. Now we're just going to take it one step further. What happens if you take the second derivative, and what's that going to tell you about a function? So first, let's just take a look at a nice basic graph, y equal to x cubed. So we have it there on our page, and we just want to look at the slopes of the tangents. So let's say we're looking at the tangents here, starting from left to right. So we start at the very left, we have a pretty steep slope. You continue along, well, look at what's happening to the slope. The slope is decreasing. I'll just write decreasing slope in this first area. Whereas, okay, eventually it's decreasing, and then take a look at this right part of the graph. So the right part of the graph, I'm just going to draw some slopes, which are very rough ones, but we can see that the slope is increasing. So what I'll say is slope decreases to start, then increases after or later. And in fact, we can see exactly where that changes. So at one point, that's bad English, at what point does the behavior change for the slope of the tangent? Well, it looks like at x equal to 0, right around there, that's where like it flattens out, but then the behavior changes. So at x equal to 0, the behavior changes. And what I mean by behavior changing is that we have the slopes decreasing, and then they start increasing at that point. And that's what we're going to focus on in this lesson is where do those changes happen? And yeah, what do these decreasing and increasing slopes tell us about the shape of the graph? And this is what we're going to call concavity. So what we say is a function is concave up on an interval if the slopes are increasing on that interval. And if we're looking at tangent lines, we'll see that the tangent lines are actually below the graph, as in the graph will always be above the tangent lines. And the second derivative will be positive. So let's just go back to that one up above. So if we're talking about concave up, you'll see that on the right side of this graph, the slopes are increasing. Those tangent lines that I drew are below the graph, so we'd say that's concave up. In comparison, we have a graph is concave down if the tangents are decreasing on that interval, and the graph will be below the tangents. In terms of a calculation, that would mean the second derivative is less than 0, actually. And you can see here on the left-hand side, those tangents are above the graph. And we started off with a steep slope, and it became less and less. And if the graph changes concavity, then we call that the point of inflection. So it's kind of the similar thing to what a critical point was, but now we're just taking it one step further for the second derivative. It's where it's 0, or it could be undefined. So you can see up above, at x equals 0 there, that's where it changes. So that would be an inflection point. All right, let's continue. So let's take a look at this function. We actually have the graph here, but we just want to do things algebraically just to confirm what the graph is telling us. So we want to determine the intervals for which the following function is concave up. So what we need to do is we need to, first of all, compute the second derivative. So we need the first derivative first, which will be 12x cubed minus 6x squared minus 12x. And then the second derivative will be 36x squared minus 12x minus 12. We want to get this equal to 0, so 0 is going to be 0 is going to be equal to that. And then we're going to want to factor. So to factor this, what you're going to want to do is, to make your life a little easier, common factor out at 12, and it's just going to be 3x squared minus x minus 1. And let's see what we get when we factor this. If you factor this out, what you're going to have is, well, you'll see it doesn't factor out nicely, and that's because I just realized a mistake. Derivative of 12x squared is 24. So let's just change that. 24x. 24 there, 24 here, 2 inside of here. Life works out a lot easier now, because now it's going to be 3x and x. We're going to have 2's at the end, so we're probably going to have a 2 here and a 1 there. This one's going to be a plus sign. That one's going to be a minus sign. There we go. 3x plus 2, x minus 1. So we have a 0 of negative 2/3 and x equal to 1. So if we want to figure out where it's concave up, what we can do, as we've done so often now, make a number line with your zeros. In this case, it's the zeros of the second derivative, so 2/3 and 1. And then test values, check the signs. That's all we're really doing. So -1, 0, 10. Doesn't matter what value you put, you're just checking the signs. And again, this is going to be the signs of the second derivative. So f prime prime is going to be, taking a look at the second derivative there, a negative times a negative, which is just going to be positive. Plugging in 0, 3x plus 2 would be, well, 2 times -1, so positive times negative is a negative. And plugging in a big number, all the parts are going to be positive, so positive times a positive. The 12 is just positive, so it doesn't change anything. It's just positive. And so therefore, the graph or the function is concave up for x an element of -infinity to -2/3 union 1 to infinity. All right, and this also confirms that both -2/3 and 1 are inflection points, because we look at our concavity, it's flipping from positive to negative, negative to positive, so concave up and concave down, switching signs there. All right, let's take a look at the graph to confirm what we actually have here. So we're saying we're concave up from -infinity to -2/3. We take a look at the graph, you can see we have this nice U shape all the way to -2/3. Then we reach approximately this point here, and that's where our inflection point is. So you can see that concave up is kind of that U shape going upwards, and then it transitions to a downwards, upside down U, you can think of it. And eventually, though, it's going to transition again. Transitions again at x equal to 1. And that point, you'll also see another transition in the shape of the graph, because now that U basically flips around again, and it's now going to be facing upwards, and it just keeps going and going and going. So there we go. So it's concave up in that first area and that ending area. Let's take a look at the next part. So what's important to note is that not all values of x having the second derivative equal to 0 are actually points of inflection. So remember, the concavity has to change. So it has to go from concave up to concave down, or the other way around. So we do have to do a little bit of a check, just like we did up above, with a number line checking the concavity on either side of what we think might be our inflection points. We also have to double check any things that are potentially undefined as well too. So things like asymptotes, holes, those matter. All right. So let's check ones where specifically the inflection point, well, potential inflection point might come from something that's undefined. And we've got our graphs too, just to help us confirm what things look like. So let's start with f of x equal to x to the 1/3. So we're just going to do some quick derivatives. Keep things simple here. So it's just going to be 1/3x to the 2/3. Yeah, and I'm just going to go straight to the answers here. Again, we'll just do things quickly here. So 2/9 x to the 5/3. Double check that for yourself, of course, too. So we've got that derivative. And if we take a look at the second derivative, at x equal to 0, undefined. There are no zeros actually itself because the numerator can never equal 0. So let's check this with a number line. So on the number line, let's just put in, well, 0. And let's test -1 and 1. If you plug in -1, well, -1 to the 5/3, that's a negative number. So it's just going to be some sort of negative answer. Plugging in 1, well, 1 is a positive number. To the power of 5/3 is just going to remain positive. So it's just a positive answer that we get in the end. So x equal to 0 is an inflection point because the concavity there is changing. And if we take a look at the graph just to confirm things, well, in the graph you can see that our derivative is going increasing, which means we made a mistake somewhere. So it's always good just to confirm things. Double check your derivatives. I did make a mistake, I realized. When I did the second derivative, it was already negative, because it would be like x to the -2/3. So it should be -2/9, which means that would be positive, that would be negative. All right. And yeah, we can see now this is concave up. It's like a U shape. The slope is increasing. Whereas when you go past that point of 0, it's concave down. And it's going like that. And you can see actually at the point of 0 itself, what's happening there and why it's undefined is that essentially we have an infinite slope there. It's going vertically straight up. And then it's changing. But just for that single point in time. All right. Let's try x to the 4/3. Let's be a little more careful with the derivative here. So we're going to have f prime of x is equal to 4/3 x to the 1/3. Don't have to worry about a negative coming down this time. So it's just going to be 4/9 to the x 2/3 negative, so that's why I'm bringing it down. And again, undefined at x equal to 0. We can do a quick check on a number line. So 0, plug in -1, plug in 1. Be careful with your work. And if you plug in those numbers, if you plug in -1, x to the 2/3, we have to be really careful here. You have the exponent 2 in there. It's fraction 2/3, but the 2 in that exponent is essentially going to, well, take away any negatives. It's like squaring something. So actually, it's going to be positive no matter what because of that squaring, essentially. And so because it's positive everywhere, your concavity is not changing. So 0 is not an inflection point. So this is why it's important to double check. Because in both cases, we had x equal to 0 not defined. But the inflection point did not exist in both ones. And yeah, in this case, since it does not change concavity. All right, and yeah, we can see here the graph it's not the most obvious, but it's a slight like U shape. Basically, it flattens out at the bottom there, and then goes up. So it is always concave up, except for the bottom part there, where it's undefined, the concavity. So we can say that's not an inflection point. Okay, so there we have it. We have seen that, yeah, we got to be careful with that concavity and checking the test for it. All right, so if we want to actually, just summarizing things, if we want to determine algebraically a function's concavity, well, its intervals of concavity, really it's all about finding those points of inflection or potential points of inflection, really. And then that's just found by setting the second derivative equal to 0, or where it just doesn't exist. Things like an asymptote or a hole. And those points will tell you the boundaries to test using a number line. So or a table, you can call it that too. But then you test the values, check where it's positive or negative, and you've got your intervals. All right, let's continue looking onwards. So we're going to take a look at some more graphs just to analyze them. So we've got this graph here. Let's identify the local extrema, as in what are the local maximums and minimums. And we're just going to ballpark. It doesn't have to be exact. We have a local max. Let's list them all at negative, 4.4 and 0.6. So again, it's just a rough guess, so it doesn't have to be precise. Local minimums, we have one at -2 and just a little bit past 3, so we'll call it 3.1, maybe 3.2. Let's just say 3.2. All right, so now let's take a look at the slopes of these particular tangents, or at the tangents for those points. Drawing the tangent, that tangent is above the graph. Same thing with this one here. So for local max, what I'm going to say is tangent above. Now let's take a look at those local minimums. Well, taking a look at those local minimums, that tangent is below. And what does that actually mean? In terms of concavity, we do actually know what that means. If the tangent is above, that means our slopes are going downwards. We're starting off with something positive, decreases, and eventually goes negative. So for local max, what that means, it's essentially concave down. And for a local min, well, the slopes are below, that means it is concave up. And we can use this just in general. So it's not just true for this graph. In general, this kind of thing will be true. And this is what we're going to call the second derivative test. So if the second derivative test, you find those potential, let's say, maximums or minimums. So those would be your critical points. So f prime of 0, c equal to 0. If the second derivative is positive, which means concave up, which has a smiley face. No, it's just actually just U shape, but that's how I remember it. It's smiley face, it's positive. Then f has a minimum, because you're at the bottom of that U. And let's just write that as a local minimum. And if you're negative, well, negative is sad, concave down, and, well, then it's a local maximum because you're at the top of that particular upside down u. All right, so there we have it, second derivative test. Very handy. You don't have to actually use it. We do know about the first derivative test, checking the slopes on either side, but this is another way to check if something is a local max or minimum. So let's try this out for a couple of questions. So for this example, we've got x cubed minus 33x squared plus 216x. We already know the critical points, so we don't have to worry about that. We just want to use the second derivative test to check, is the point at x equal to 4 or x equal to 18 a maximum or a minimum? So again, we'll just have to do some quick derivatives. So we're just going to get 3x squared minus 66x plus 216. And the second derivative is going to be 6x minus 66 plus 216. And then we want to do some factoring because we want to find out the zeros. And also, plus 216 does not end up in there. Yeah, just doesn't. Okay, so we got the second derivative. That's all good. Okay, now we want to use the second derivative. So we don't even need to factor. We're just using the second derivative test. Although, in general, it's usually good to factor just because knowing where those inflection points are is very handy too. So let's test x equal to 4 and x equal to 18. We'll just do them separately. So what is the second derivative of 4? Well, it'll be 6 times 4 minus 66, or 24 minus 66. I can already see this is going to be negative. Let's just get an actual number to that, negative 42. So therefore, at x equal to 4, we have well, it's negative. So think negative, think sad, think, well, top of the sadness part is a maximum. And then x equal to 18. So f prime prime of 18 is equal to 6 times 18 minus 66. That's going to be bigger than 0, but let's just get an actual number to that. So 6 times 18 is 108 minus 66. And that's going to be 36 plus 8 is 44, I think. Therefore, at x equal to 18, it's positive. Positive people are happy. So we're at the bottom of the smiley face, so we have a local min. Okay, and there we go. So that's how we use the second derivative test to check if something is a local minimum or a local maximum. Lastly, we basically want to put together everything we've done in the past couple of days now. And this is really going to be the essence of kind of this portion of the unit, because we're going to use all of this in the upcoming days to actually sketch some graphs more accurately. So we have a function here. We want to figure out what are the x-intercepts, what are the critical points. We want to figure out where is it concave up, where is it concave down, and we want to figure out, do we have maximums or minimums. So we're getting all this extra information now about these graphs to make them as accurate as possible. So starting things off, x-intercepts. We always use those when drawing graphs, originally of polynomials. We still want to use those. In this case, we have the factored form there, so it's just going to be x equal to 2 and x equal to negative 1. And well, the x equal to 1 is order 2. Okay, now we want the critical points. So let's work on b down here. F prime of x is going to be, all right, so here we go, taking the derivative. It's going to be 3x squared minus 6x. Well, and that's it. And let's get that factored. So that's going to be 3x, x minus 2. So our zeros are going to be, so set it equal to 0. And our zeros are going to be x equal to 0 and x equal to 2. Okay, so those are the critical points. There's nowhere it's undefined. So therefore, critical points are x equal to 0 and x equal to 2. Okay, let's continue onward. So now we want to figure out a little bit about the concavity of the function. So we need the second derivative. So the second derivative, I'll go off the expanded form. That's always usually the easier way to take derivatives. So 6x minus x, factoring that is just 6x minus 1. So we kind of have our important point of x equal to 1, maybe an inflection point. So what we do want to do is set up an interval, number line, at x equal to 1. And then on either side, I'm just going to put a 0 there, 10 there. It doesn't matter. Just plugging in numbers into that function. It's a very simple function, so if you plug in 0, well, 0 minus 1 is negative, so the whole thing is negative. If you plug in 10, 10 minus 1 is positive, so the whole thing is positive. Right, so that does confirm, yes, x equal to 1 is an inflection point. The concavity is changing. Not only that, it is concave up for x an element of, well, 1 to infinity, and concave down basically before that for x an element of negative infinity to 1. So we have those two pieces about concavity. And I think the last part, let me just scroll back up, make sure I'm answering the questions, is, well, to state what the critical points are. So the critical points in this case are, well, they were 0 and 2. So now if we do our second derivative test, f prime prime of 0, well, we have our intervals. So we can just say f prime prime of 0 is negative. So it's concave down. So I always like to just picture it. Again, it's not about just memorizing different cases. Have an understanding of what does it mean shape-wise, and that will help you to remember if it's a local max or a local min. So remembering what concave up and concave down actually means, that's probably better than just trying to memorize the second derivative test in the cases. So concave down just means it's an upside down u. So then x equal to 0 is a local max, because it's the top of that u. And the second part, f prime prime, I think it was 2. Yeah, it was 2. F prime prime of 2, well, that is going to be greater than 0. Again, using our little number line up there. So greater than 0 is happy. It's like a smiley face. And so x equal to 2, we'll set the bottom of that smiley face. So it is a local min. And there we have it. So we just found out a whole bunch of information about that function. And as we move forward, we're going to use all this extra information to draw, well, the best kind of graph possible.